Yeah, thank you very much for the introduction. Again, my name is Anton Odermatt. I'm from the Helmholtz Center here in Germany. This is a joint effort of my department, Laser Processing and Structural Assessment, from the Institute of Material and Process Design, as well as the Department of X-ray Diffraction with Synchrotron Radiation from the Institute of Material Physics. I would like to thank all my colleagues who distributed to this work, especially the beam scientists Guilherme and Sebastian. This is my agenda for this talk. I will start with a brief motivation for this project. Then I will describe the methods, mainly the additive manufacturing setup and the residual stress determination. Then I will briefly cover the resulting microstructure we obtained and give a detailed analysis of the residual stress field in our parts. And I will finish with the conclusion, and I hope that I can answer some of the questions afterwards. As a department, we are in contact with a lot of companies manufacturing parts for the chemical, pharmaceutical, marine, and hydrogen industries. Like all others, they are facing increasing pressure to reduce manufacturing costs. And a lot of these parts they make are currently made by machining 90% of the volume or more. And therefore, additive manufacturing is an interesting solution to reduce manufacturing costs. What all of these parts have in common is that they are facing a combined load from mechanical pressure and also other factors such as temperature, corrosion, hydrogen embrittlement, or wear. As we all know, these additional loads also interact with residual stresses, and the severity of these additional loads is increased. All additively manufactured parts also have inherent residual stress fields from the sequential addition of material and from the inhomogeneous temperature fields and cooling rates during their creation. Therefore, this stress field distribution needs to be considered at the design phase and mitigated or engineered in such a way that it is not detrimental. As a material for these applications, we are currently investigating the use of duplex stainless steel, mainly because it has superior mechanical properties when compared to the conventional austenitic stainless steels, almost 2.5 times the yield strength, comparable ductility, and superior stress corrosion cracking resistance. The origin of the superior properties of this material is in the duplex austenitic ferritic microstructure, which needs to be kept at a balanced ratio of approximately 50-50, where the ferritic phase increases the strength and the austenitic phase increases the corrosion resistance and toughness. This is our manufacturing setup. The specifications are given in the upper right. We use laser-directed energy deposition with wire. The processing parameters are given here. We investigated the stress fields of two different processing strategies. We started first with a layer-wise build strategy, where we manufactured a simplified pressure vessel geometry in a layer-by-layer manner. Here we chose in track order from the inside to the outside, and the idea is that the sequential addition of material will place the innermost layers under compressive stresses, which is the media-facing side. To prevent the heat build-up, we adhere to an interpass temperature of 300 degrees Celsius, except for the deposition of the innermost layer, where we skip this interpass temperature to achieve reduced cooling rates and increased austenite formation. Because we were not fully content with the residual stress distribution this strategy produced, we investigated the second build strategy, which we call the cladding build strategy, and which was also shown in the video. Here we produced first the inside wall and then put 2 additional clad layers on this part to achieve the final wall thickness. And during the deposition of this part, it was cooled using sprayed water. The residual stress determination was done via the incremental hole drilling method, where we used a prism system by Stress Tech equipped with the electronic spattle pattern interferometry to measure the relaxation strain. This will be used to compare the residual stress fields of the two processing strategies, because we could only obtain beam time at the P61A station for the investigation of the first specimen. The P61A station is a station where polychromatic radiation is used to characterize materials and residual stresses. What's special about this is that there is a detector at a fixed 2 theta angle, and an energy dispersive spectrum is measured. the incoming and diffracted beam are limited by a system of apertures where such an elongated gauge volume is created. And in order to get good peak separation between the austenitic and ferritic phase, we have to use a very low θ angle, which increases the aspect ratio of the gauge volume. To keep it smaller, we have to then decrease the size of the apertures, which means that we have only a very small gauge volume, which leads to bad statistics in the measurement. And we have to compensate that by wiggling of the gauge volume across some area of the sample. The stress determination is done by the evaluation of the peak shift position in the energy dispersive spectrum that we measured, where the peak position can be correlated to the lattice spacing using Bragg's law and the relationship between energy and the wavelength. And to calculate true stresses using this method, the stress-free lattice spacing needs to be known exactly. And we measure this on such a prepared sample where we cut stress-free lamella using the same processing parameters, and then we can have location-dependent stress-free lattice spacing. This is the resulting microstructure of the layer-wise build strategy. The microstructure is here dominated by these epitextually grown ferrite grains, which grow across multiple layers in the upper parts of this material. Here we observe similar austenite contents in all tracks, but we have a slightly increased austenite content here on the inside track, which is what we hope to achieve. We also observe some increase in ferrite content near the top, which is caused by the lack of reheating by a subsequent layer. And also we have slightly increased austenite contents at the bottom, which is caused because here in this region, the epitextually grown ferrite grains have not yet eliminated the slow growing ones yet. And we have an increased amount of grain boundaries where the austenite can precipitate from. For the cladding build strategy, the microstructure looks a bit different. In the inside track, we have, again, here these epitextually grown ferrite grains, but a much increased austenite content. And this is because we have a reduced cooling rate because all of the heat from the melt pool has to be conducted through a relatively thin wall. And also in the clad layers, we see a reduction in the size of the ferrite grains. And this is also due to the changed heat flow and solidification direction where the epitextual grain growth is suppressed. In summary, we also observe a much higher difference in austenite content, which is really nice because then on the inside we can have increased corrosion resistance, and on the outside where we don't have these additional loads, we can have increased strength. This is the residual stress distribution we measured on this part. So what we expected is that we kind of have this residual stress distribution where the outermost layers are placed in tensile residual stress state because the thermal contraction is hindered by the already deposited innermost layers. And this is also what we can see here in almost all locations where we have a trend of the residual stresses going from tensile to more compressive. And also we can kind of see this residual stress distribution in the X direction when we look at the side of the sample, where we have residual tensile stresses from the last deposited material or in the last deposited material and compressive residual stresses near the base. This stress distribution causes a kind of bending deformation of the whole part, which induces here these tensile residual stresses near the edges on the outside in the Z direction, which can also be observed in the measurement. And then these need to be balanced by compressive residual stresses near the center faces of the part. Overall, we have very high residual stresses approaching the yield strength of the material, which is approximately 550 megapascal, especially in the upper parts of the part, and also near the inside facing wall, which is why we changed or tried the second processing strategy. These are compared via the incremental hole drilling method, where here the results for the cladding build strategy can be seen. Interestingly, we have, it's important to keep in mind that while on the last slide we had a measurement of the whole wall width, here we can only measure the first millimeter or the residual stresses in the first millimeter. So we have a slight increase from the outermost surface to a maximum and then a decrease in the residual stresses, which we also saw in the synchrotron measurements. But what is interesting to see is that when we compare all the locations individually, nearly everywhere we have higher residual tensile stresses produced using this cladding build strategy on the outside, which makes us believe that these need to be balanced also by higher compressive residual stresses on the inside of the part. So in conclusion, we learned a lot about the evaluation of stresses in duplex stainless steel using synchrotron radiation, which is very difficult to do due to the large grain size of the prior ferrite grains, strong texture, the dual phase microstructure, and because we have high absorption from the high wall thickness. That the order of layers and weld tracks has an influence on the residual stress state and the microstructure, and they must be engineered to achieve optimal results. And that the material which is deposited early in the process is almost always placed under compressive residual stress, while the last tracks are in a tensile residual stress state. And I think what is really important to take from this is that when we have this manufacturing setup with more than 3 axes, we can not only use this to make complex parts, but also use it to tailor the residual stress field and the microstructure in the part by changing the heat flow direction. As an outlook, we want to acquire additional beam time to measure stresses for the second processing strategy and also investigate how the stress states affect these secondary loads, such as corrosion, hydrogen embrittlement, fatigue, wear or tribo corrosion, and the damage tolerance. We are currently working on fatigue, where you can see that we get very uneven fatigue crack propagation in these samples. A colleague of mine who has a talk on Thursday is working on hydrogen embrittlement, and if anyone is interested in working with us on the topics of corrosion or wear, then please feel free to contact me. Yeah, this is some sources for the pictures, and thank you for your attention.